Hi folks, welcome to this second video on similar shapes. Today we're looking at similar areas. We're going to be using a lot of the same skills from enlargement and reduction, which is on the previous video. So if you haven't watched that, go back and give that a quick watch first. We are going to be looking today at how we can take an enlargement or reduction scale factor and convert it into an area scale factor. I'll explain a little bit about how that works as we go through this first example. Let's just do what we know how to do. Let's see if we can find an enlargement or reduction scale factor for these two rectangles. Okay, so what we do, we look and see what shape we are being asked something about, and we can see over here we've got X. This time it's not on a side, it's in the middle, so we're being asked to find the area of this rectangle. How much space does it take up? Okay, but it's on the big shape, so this is an enlargement scale factor question, which means from last day we're going with big over small. Okay, we're going to be using side still to do our comparisons. So here we've got the 4, which matches up with the 12 from the bigger rectangle. Okay, the big number on the top, 12, small number on the bottom, 4. Simplifying that down where we can, 12 divided by 4 gives a really nice scale factor of 3. Okay, that means that this rectangle, in terms of its sides, is 3 times bigger than the small rectangle. However, what happens with areas is something slightly different. If I enlarge all the sides of a rectangle by 3, so this side's 3 times longer than that one, and this one's 3 times longer than that one, I'm actually increasing its size by 3 in that dimension and 3 in that dimension. And actually this results in not the area getting 3 times bigger, but 3 times bigger twice. Okay. How do we process that mathematically? Well, what we're going to do, we're going to take our enlargement scale factor and we're going to find an area scale factor. I like to call this the ASF, area scale factor. It's a really simple process. The area gets 3 times bigger twice, or by 3 squared. Yeah, remember, if we multiply something by 3 twice, this is the notation that we use. So it's 3 squared, okay, which means our area scale factor is actually 9. The area of this big rectangle is 9 times the size of the area of the small rectangle, okay. So let's try and do our little calculation. Now it's very similar to last day. I want to find X, which is an area. To do that, I take my area scale factor, not my enlargement scale factor, and multiply by the corresponding measurement from the first rectangle, which in this case, the area of this one is 8. And 9 times 8 gives me that the area of the big one is 72 square centimeters. Not 3 times bigger like you might think, but 3 times and then 3 times again bigger, okay, because it's acting in 2 dimensions. Okay, let's try another example just to cement that idea. So here's example number 2. Okay, we've got a couple of trapezia here and we are trying to find the area of this one. Which one is that? Is that the big one or the small one? It's the big one, which means I'm going to start with an enlargement scale factor. Okay, enlargement scale factors. Hopefully we're pretty good at this now. Big over small. Again, we're using the length to find the enlargement scale factor. So I've got a 6 from this one and an 8 from this one. And the big number goes on the top, so 8 over 6. Not a particularly nice division this time, and like the last video, I'm going to try and do everything with fractions where I can. So dividing top and bottom by 2 gets this fraction as simple as possible, and it becomes 4/3. Okay, this scale factor does sides only, not areas. To find the area scale factor, you are going to take the enlargement scale factor, which is 4/3, and like the last one, we are going to square it. Okay, bit trickier this time, right? I mean, like, how do you square a fraction? Well, thankfully it's really quite straightforward. All we do is we square the numerator and denominator. Now remember, squaring isn't doubling, squaring is multiplying by itself. So this 4 is going to become 16, 4 times 4. And this 3 is going to become 9, 3 times 3. Okay, so we're just squaring to find the area scale factors. Once I've got the scale factor that applies, I'm just going to do a quick calculation with it. So I want to find x. X is equal to the scale factor multiplied by the equivalent value from the first trapezium, which is the area of 18 square meters. Okay. How do I find 16/9 of something? Well, I take the 18 and I divide it by the denominator, which in this case is 9. So 18 divided by 9 gives me 2. I then multiply that answer by the numerator, which is 16, and that gets me an answer of 32 square meters. All right. So same process, you can see the same working going on here. Find the scale factor, whether it's enlargement or reduction. To make it apply for areas, we have to square it and then we use it. Okay, last example. Here we've got two triangles. I need to think, am I finding an enlargement or reduction? And I can see the x appearing on the smaller triangle here. So this is a reduction question. So we're going to start by finding the reduction scale factor. Remember, only difference with this is that it's small over big instead of big over small. Small over big. What do I mean by that? I mean, we take the two corresponding sides from your triangle and we put the smaller one on the top. So in this case, 3/5. Again, you could simplify that down using a calculator or to a decimal of 0.6, but I think the fraction's really nice to work with. So we've got 3/5. Okay, what we've got to do now, we've got to find the area scale factor, okay, the ASF. So the area scale factor is equal to this reduction scale factor squared. Okay, how do we square? We square the numerator and square the denominator. So 3 squared is 9 and 5 squared is 25. Okay, we're nearly there. We've got our calculation to do now that we know the area scale factor. So we're looking for x. It's equal to the scale factor multiplied by the corresponding value from the other triangle. So in this case, 75 square meters. Okay, looks quite complicated, but if we give it a wee bit of thought, we can see this is quite straightforward. We're taking our 75, we're dividing by the denominator. How many 25s go into 75? I think this is easier if you count it up, yeah? So we've got 25's 1, we've got 50 is 2, and we've got 3. Lots of 25 makes 75. So we're at 3 from doing the division. We've got to multiply that by 9. Gives me that the area of the smaller triangle is 27 square meters. Okay, one more video to go on similar volumes, and that'll hopefully give you a good head start for your learning today.